Hello and welcome back. We're going to look at 2023 day 3 here. Um, let's get into it. So again, a lot of flavor text, but basically we can sort of tell what's going on by the input. So your input is kind of a matrix of strings here. Each one of these will be on its own line. And we have 3 types of characters in this matrix. We have numbers, which are, they're kind of like read left to right. So if I was parsing out this matrix and I wanted to pull out the numbers, I couldn't just like look at each one individually. Instead of a 4, a 6, and a 7, this would be 467. This would be 114, et cetera, et cetera. So when we're parsing these, we kind of have to look at each line and read left to right. So that's one type of character in here. We also have periods, which are essentially empty space and can be treated as such. And then we have a variety of symbols. The symbols that are actually used aren't spelled out anywhere, but it's just like, just look at the top row of your keyboard, press shift, and you'll probably get the alphabet. So for part 1, it basically says, so for each character in this matrix that is a symbol, we want to take the numbers that are adjacent to those. And adjacent means not just horizontally and vertically, but diagonally as well. So for example, this plus character, the 592 would be adjacent to it. But 114 here doesn't have anything adjacent to it, so it doesn't count. So we find all the numbers that are adjacent to any symbol, and we add all of them up. And then part 2 says, okay, actually, we just care about these asterisk symbols. They're calling these gears. And we want all of the gears where each one has exactly 2 numbers next to it. And then for each gear, we want to multiply these numbers together. And then we add up all of the products. And that's part 2. So I think there's a couple different ways to solve this. But yeah, let's get into it and see what we can do. So we're going to be using APL for this one. We'll start with the test input, and then as usual, we'll move on to the full problem input. So we get a list of lines here, and because they're all the same length, we can mix them together to get a matrix of characters. And we'll assign this to P. And then it's also going to be useful to get a flat vector of all of the characters in P. And we'll assign this to like R for rows. Basically, in this problem, we're going to be sort of working with 2 different representations of the data. There's going to be a matrix, and then there's going to be like a flat vector of everything. And some operations are easier in one in one configuration than they are in the other. So we'll kind of switch back and forth. So I think there's a ton of different ways to do this, but the plan is basically what would be really cool is if we can get for each point on this matrix, if we could get the numbers that are adjacent to that point. Again, either horizontally, vertically, or diagonally. And then once we have all the numbers that are reachable from each point, we can basically do some filtering. So for example, we could filter the points that contain any symbol for part 1. And then for part 2, we could filter to only asterisks and then make sure that the points that are reachable from that set are only of length 2, right? So this is sort of the general plan. First, let's start off working in the vector representation of our input. So we have our row, and then we can say which one of the characters in here are digits. Quad D, I use this a lot in my videos, just gives you a string of the digit characters 0 through 9. And we get a Boolean vector, and we can say it would be really neat to be able to assign each of these numbers like a unique ID, so that when we go through the matrix later and we're trying to figure out which numbers are adjacent to a particular point, we can use the unique IDs to be able to reference those numbers. So one way we can do it is we can do a pairwise reduction to get, rather than having ones for all of the characters in a particular number, we just want a one where a particular digit starts. So we can prepend a 0 to this, and then we can do a windowed reduction to wide less than. And all this is doing is it's looking at each pair of the vector and determining whether the second element is greater than the first element. And this only occurs at sort of the start boundaries for numbers. And we prepend a 0 because when you do pairwise reductions like this, you lose an element. And we also want if you look at our input, we have a digit as the very first element in our matrix, and then also in our vector. So we want to make sure that we have a 1 there. Okay, and then so given this, we can do a plus scan to sort of run a cumulative sum from left to right. And this does give us a unique ID for each number. So each time that a number starts, you get an increment, and that increment keeps going until it gets to the start of the next group. However, we want some way to, this vector isn't very useful for selecting particular digits because it includes empty space. So we can assign this to maybe like D for digits. This is just, again, this is just which characters are actually digits in our vectorized form of the input. And we can multiply that by this cumulative sum. And this way we get zeros where there's empty space, and where there's digits, we get the unique ID that gets assigned to it. Now, it would be, because we're going to be doing a matrix operation on this, it would be helpful to reshape it into a matrix. And so we stored our matrix of characters first. We can get the shape of that via P. In this case, it's just 10 by 10. And we can use the shape of our input to sort of put things back into matrix form by doing reshape here. And now you can see, so if we look at this and if we look at our input, you can sort of see where the digits occur in the matrix. We have unique IDs assigned to them. It's just one counting up, basically. And then zeros are empty space, right? So this will be quite helpful. And now we have a chance of, basically for each space in the matrix, we can look at the surrounding elements, we can remove the zeros, and then we get a list of the numbers that are reachable from that particular point. Speaking of the numbers, we'll assign this to M real quick for matrix. So we have a Boolean vector of digit characters, and we have our vectorized form of the input, which means getting the actual digits themselves is as easy as just doing partition here, right? And then for each one of these, we can execute to get actual numbers, and we'll assign this to like in for numbers, I guess. Naming is hard. Okay, so if we go back to our matrix, we have unique IDs for all of the digits. When we're talking about operations like, okay, for each point, I want to look at all of the surrounding things and I want to perform some operation on those. The thing that you want to be reaching for is stencil. Stencil is super useful, especially in like cellular automata problems that occurred in previous advents of code, and is probably going to appear again this year, so keep an eye on this one. But basically what this does is it takes a sliding window of a size that you specify and applies it over a matrix or really an array of any rank. And note in the example here how there's like zeros at the corners. So it will look at spaces on the edges, and it will fill in things around the edges. So in this case, because you're working on a numeric array, it fills in zeros, which is great for us because we're considering zeros to be empty space anyway. So let's use symbol. So we're going to operate on our matrix. We are going to take 3x3 sliding windows, and we're going to run a function on those. First thing we want to do is just flatten everything. So rather than being in matrix form, it's just going to be a vector of 9 elements. And we want to remove the zeros. This is the without function here. Because zeros are empty space, we don't really care about them. Next, let's take the unique set of elements that are left over. And actually, I'm not even sure that you need unique. We'll test that in a second. And then we'll enclose it to put it into a box so that these all fit into a matrix. And now you can see that we get a matrix that's the same size as our input, but for each space, we get the IDs that are reachable from that particular point in the matrix, right? So pretty cool. The interesting thing about the IDs, by the way, is because the IDs start at 1 and count up, and we're in index origin 1, the IDs actually exactly correspond to the index of the actual number in our number vector here. So we can just index into the number vector here rather than the IDs, and that gives us the actual numbers that are reachable from any particular points. And we can just do a quick spot check. So 467, 114. Yeah, this all looks correct. And then in the second row here, there are some spots where you can reach both 467 and 35. So that also looks correct. Okay. Let's call this first let's put everything into a vector. Let's flatten it, and then let's assign this to G for groups, I guess. So now both part 1 and part 2 become quite easy because basically we're just putting together Boolean vectors that select on G here. So for part 1, we are interested in symbols, meaning that they are not period or digit characters. So we can put together a string which is periods concatenated with all the digit characters, and we can say the flattened form of our input is a member, not. So this selects for all the elements that are not a period or a digit character, and then that results in a Boolean vector, so we can select on G, and that gives us all of the numbers that are reachable from those points. We can enlist to get all of those numbers out of their boxes, and we can add things up to get 4361, which for part 1 is the answer. For part 2, we have sort of 2 criteria that we want to select on. So first, we want the elements in our flattened input that are equal to asterisks. This gives us a Boolean vector. And then we want the elements of G that have a length of 2, right? And because these are just 2 Boolean vectors, we can just AND them together. And then we can take the resulting vector, and again, we'll select on G. For each element in G, we want to multiply the numbers together, and then we just add those to get 467,835, which is the answer for the test input in part 2. If we look at the whole thing, it looks like this, and this is pulling the actual input. So we can attempt to run this real quick. And we get 525,911 and 758,05607. It's the correct answer for our input for part 1, and the correct answer for part 2. So, yeah, I guess the moral of the story with this one is, first of all, working with data in different representations based on the operations that you want to perform on it. We sort of operate on the data both in matrix and vector form. We need to do the matrix form and to be able to use stencil here. Otherwise, we just want to use vectors so that we can do simple like Boolean selections. And then this answer is not particularly efficient because we're creating a bunch of boxed vectors in our group here. But for the size of the actual inputs, we multiply these together, and it's just under 20,000. Just under 20,000 cells in G, I suppose. So not really to the point where we need to optimize here. But I'm sure that there are more efficient solutions. This just happens to be the one that I use, and I think it's pretty concise, and it makes part 1 and part 2 very nice because you're just basically putting together Boolean vectors and selecting groups. So that is day 3. Yeah, hope you enjoyed watching. Stay tuned.